All right. Good evening, everyone. Glad to have four of you. Al is not going to be here because he couldn't take the class, and I think they kick him out of Zoom.us. Hey, Al, I'm going to send this tape so you can enjoy yourself if you have 1 hour doing nothing and you want to fall asleep. That's the video. But this week we are studying properties of stars. It's an important subject. I think is the second most important topic in astronomy in ASTRO 10, besides the chapter on light. So we learn what light is, and then we study about properties of stars. And it's a continuation, I can say. So that's what we're going to do today. But before that, I would like to talk about two things. One, we had a discussion on this strange exoplanet. Um, so if you go to the history of exoplanets, how they were found, the very first exoplanets that were found and discovered and announced, they were Jupiter-sized exoplanets. They were not like Earth-sized exoplanets. As you study in the book, you realize the largest population of exoplanets are in the low range, the low size, super Earth, if you will, but not Jupiter. So how come you find the Jupiter size first? It's because of the technique they were using. They were using a Doppler effect, and the Doppler effect technique implies that you are able to detect a wobbling motion of the star itself. So the star is being pulled by the planet nearby, and in fact, our sun is pulled by all the planets, and there is a simulation. I, 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 I will not pull out now, but if somebody asks, I can have it ready for next week. There is a simulation that shows how much the sun wobbles as a result of the tug war with each of the planets. And of course, Jupiter is the one that gives the most motion in the sun. And motion in astronomy is always translated into change or shift in frequency, which we call Doppler effect. Um, so the first technique used was Doppler effect. Basically, they took the stellar spectra with a very sensitive array of emission lines or reference lines, and by doing so, they were able to detect the motion of the star with very good precision. And 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 the strange thing was that most of these planets found, the Jupiter-sized planets, were found closer to the star than Mercury is. So, and then we studied solar system formation or formation of the solar system and star formation, and we learned that planets in our solar system are segregated into terrestrials and gas giants or Jovian planets. So the terrestrials are closer to the sun and Jovian are further out. And one of the discussions we had before was how this happened. And then the clear answer was that most of you answered was the sun's heat. The sun's heat prevent ices to be formed in the region closer to the sun, and then most of the grains formed are rocky type or metal type grains. So all the bodies that are formed out of these grains become solid, and whereas the regions further out are the regions where the volatiles and ices are formed, and so Jupiter, Uranus, Neptune, and Saturn are planets whose major chemical abundance is hydrogen and helium, um, as opposed to iron, silicon, and oxygen as we have here on Earth. Um, and all of these differences between the planets are the result of the sun's heat, basically. The material that formed the solar system and the planets originally were the same, but once the sun was formed and in place, it segregated and it formed the solar system that way because of its heat. And then how come we start finding all kind of Jupiter-sized planets in a region that even closer to the sun than Mercury is. So that was the key point. And the answer to this question is migration. That's the key word, migration. Migration, not immigration, migration. So the idea is and has been supported by, in fact, is a theoretical approach, but has been supported by some good evidence, is that these Jovian-sized planets are formed further out. But when they are formed, the disk that formed them is still populated by all kinds of materials. And these Jupiter-sized planets interact with this material. And this interaction allows them for losing potential energy or gravitational potential energy, and then slowly they migrate inward. And then eventually they are pretty much settled in a region that is very much close to their parent star. Now, as they do that, they might or might not disrupt the entire star system. So imagine if you have a planet like Earth, and then suddenly you have a big Jupiter coming in and interacting and doing all kind of crazy things. In our own solar system, you might have learned in previous chapters, the gravitational tug war between Jupiter and Saturn were the responsible for the creation and settling of Oort cloud and the Kuiper belt. And also, they slingshot lots of ices to the inner regions of the solar system, and they might have been responsible for providing us with a large percentage of water in our own planet. So water we are drinking might have been water provided to us by material formed in regions closer to where Jupiter and Saturn originally were formed. So migration, that's the point in the discussion that I want to mention to you, and it's going to be the exam. So let's talk about exam. So exam is this Thursday, is the second one, and goes from the chapter that deals with the light and telescope all the way to the sun. With the chapter we deal and we studied last week. I try. I still using questions that I've been using before, but I review them and I make sure they translate into subject we studied in the book. So I had a couple of students mentioning they find some of the questions out of sync with what they read in the book. I think this is mostly true for the homework, but I try to review and to scrape off the midterms from these questions that are not necessarily associated with the book. But in particular, I went to the book and I select some questions from the end of the chapters. I grab a few questions and I create multiple choice options, and they are in the exam as well. So I think you feel more comfortable with midterm 2 than with midterm 1. You still can do at home using Proctorio, as long as you have a Google browser and Proctorio extension installed in your Google Chrome. And you have to have a camera that it's going to be enabled in the beginning of the exam. You must be alone in the room that you are doing the exam. You have to show identification. You have to show your cheat sheet. I allow one page back and forth of notes, so you can do that. You and then what else? And the exam lasts 1 hour, and you have the entire Thursday to do that. I will reopen the exam on Saturday. I will be proctoring the exam Thursday afternoon in room SA115. So if you go to room SA115 in the Math and Science, Math and Science and Social Sciences new building, in room SA115, I will be there. And then start at 4 sharp, and must be closed sharp at 5, since I have classes right after. Okay. You don't need to bring Scantron. Make sure you bring identification, and pretty much that's it. So, any question regarding exams? All good. All right. Okay. Wonderful. So that. So let's go over brightness. So there is a major difference between these two terms here, brightness and luminosity. So luminosity is a term that gives the amount of energy the star itself sends out per area and per time. So when we think about luminosity, it's more like a power of the star per square inch, if you will. So a star is luminous if produce um, sufficient amount of energy per time, which is power, in a given area, per area. And luminosity is a quantity that is different from brightness. Brightness is what you see. So you might have a very luminous, which means energetic star, that is way far away, 500 light years away. And you might have a star that is somewhat closer in our neighborhood, and we won't see it. So, and a star that is luminous, very luminous, that is 500 light years away, because it's luminous, because it's very energetic, we can see it. Like any supergiant that is significantly close by, less than 1,000 light years, we might be able to detect it. But all the small stars, M stars, as we say, they are in our neighborhood, we don't see them. They are too faint to be seen. So brightness is the amount of energy we receive, and luminosity is the amount of energy the object itself sent. Is that okay? Got that one? And apparent brightness is the name is saying, is how apparent bright these stars are. It doesn't tell what we call intrinsic or luminous. Intrinsic brightness in some books, it's termed the energy of the star itself. It's kind of confusing. So one is intrinsic brightness, the other one is apparent brightness. And I think the main point is to distinguish, um, and I prefer to do that way, to call brightness is what you see, and luminosity is what comes out of the star as far as energy is concerned. Both of them are related to energy, but brightness is what you detect here, and luminosity is what is sent out. If we had all the stars at the same distance from us, right? Then the brightest stars we see, attention what I'm saying, if all the stars were at the same distance from us, right? It's kind of a crazy idea, but imagine you can take the trillions of stars out there and put them at the same distance from us. So if we could do that, the brightest of them all would be the most luminous. Then the two terms would match, right? But not necessarily. Since they are at all kind of different distances, we might have a somewhat bright star or somewhat not luminous star that is very bright. Here's the example: our sun. So our sun is a star that is the brightest one we have in the sky, right? So bright that we can't see the stars in the daytime. But the sun is not the most luminous of them all. The sun is not the most energetic star in the sky. Just give me 1 second. Just 1 second. I will be back in a second. Just a second. Okay, back. Now, the brightness gave rise on a scale that is called the magnitude scale. The magnitude scale is a logarithmic scale, and we do not go over these details in our lecture, and we also don't go in details in the lab either, but suffice to say that what astronomers do, they select a group of stars in the sky that are supposed to be standard. So they don't change much over time, and then they compare the brightness, as we see the apparent brightness of stars in the sky, to the brightness of these standards. And by doing so, they have a reference, they have a scale, and that scale is in logarithmic. And I know no one uses logarithm anymore, but it was largely used in the 1800s, and then we still have it. And the magnitude is translated in numbers, and the numbers are readable. They are nice. So look at this. Because of this logarithm scale, it so happened that the biggest the number, the faintest the source is. See that? So for instance, the sun is out here. It's the brightest object we know, but it's also the one with the least apparent magnitude. It's somewhere negative 25, 26 or so. So it's the negative scale. Now, the limit to what we can see is right here. The limit to what we can see is the number 6. So stars, they are fainter than magnitude 6. For instance, a star that's magnitude 7, we can't see it. We need a telescope, or we need a binoculars, we need something. So Betelgeuse is a supergiant. So Betelgeuse, we can see it, and it's extremely bright. We can see in the sky in this constellation Antares, no problem. Sirius is the brightest star in the sky, and Sirius has a magnitude scale between -1 and -2. I'm kind of guessing here. Look at Jupiter and Mars, very bright too, but they are not energetic compared with the stars out there in the sky. So again, this apparent magnitude scale is a scale logarithmic, and what you need to remember is that the smallest number indicates the brightest object as we see in the sky. Colors. So we saw the scale, the energetic part of it. Now, in the 1800s, more in the field, in the front line of physicists that were attempting to understand what atoms, the building blocks of nature is, what exactly light is, they found a tight correlation between brightness, in fact, between color and surface temperature of stars, and the scale is in the following. So if you think of a star that is extremely blue out there in the sky, like Spica, this star has a surface temperature in Kelvin scale, which is 25,000 Kelvin. So Vega, which is a kind of a whitish star, is a little bit cooler, 10,000 Kelvin. Look at the sun. The sun is somewhere here. The sun is a yellow star, and the sun has a surface temperature of about 5,800 Kelvin. And then you go to stars that are even cooler, 3,000 Kelvin, like Betelgeuse. You look at Betelgeuse in the sky and you can't miss it. it has some orange or reddish coloration. And just by looking at it, you can establish this correlation between color and temperature. And a physicist, what I'm trying to do here, let me see if I can. So you look at Betelgeuse right here. Even this is a simulated sky, but you can tell how kind of the color is not the same as Sirius. This is Sirius. So Sirius is a 10,000 Kelvin as we. Oops, I didn't get Sirius, did I? So Sirius is right there, is a star that is an A star. We are going to study stellar spectral classification, but the apparent magnitude, see the number over there, negative 1.47. Negative 1.47. Let me see, somebody's trying to.
And we can't see your screen.
You mean, oh, somebody is at zoom.us. I don't know who that might be. Probably one of you, or is trying to in the wrong place maybe. So Sirius is negative 1.47, very bright.
Look, can't really see the screen, the one you're talking about right now.
Oh, it's not coming the screen. Oh,
no.
Okay, wait a second. So I have to probably to expand my sharing capabilities here. Thank you, Rick. How about now?
Yeah, there we go.
There, yeah.
Okay, so this is, again, Sirius, right? So Sirius has a magnitude, look in the top left-hand side, is a negative 1.47. It's an A star, and that negative number indicates how bright that star is. Let's see, Betelgeuse is a K star. So K star is a cooler star, and then you can see it with this kind of an orange coloration, but the magnitude is 0.43, which indicates it's less bright than Sirius because the number is slightly bigger. So let's take a fainter star right here, and then you can see that one over here. So that star, the magnitude is 1.62, is a B star, is a hot star. How about this red star right here? Probably is an M star. Right where my hand tool is. Right there. See this red star right there?
Yeah.
So that's an M star. M is the coolest star. So check the magnitude, 4.28. Let's take an even fainter star. This one over here. 7.46. So as you go to fainter and fainter sources, the magnitude that represents how bright they are indicates bigger and bigger number. Look at this one, 8.43. I can't say much about color. But anyway, the main point that I want to highlight is this correlation between color and temperature. The bluer, the hotter. The redder, the cooler the star is. Now, this is a very interesting piece of history because now we have the spectral classification, and in the spectral classification, we owe that to remarkable work of women and after in the turning of the 20th century. And your book gives a nice history of it. Now we have these O, B, A, F, G, K, and M. It's a nice way to memorize. It goes in all books, even in Brazil, of all places. O, B, A, find girl or guy, so whatever you like. Kiss me. That's a great way to remember. So O are those hot stars, and N are the coolest possible stars there is. And the classification is now in such a way that besides those letters, you have numbers in between them. So the hottest possible star is an O0, and then it goes O0, O1, all the way to O9, and then B0, B1, all the way to B9, and so on, so on, so on. And they found there are stars that are even cooler than M stars, 3000 Kelvin. They are classified as L, T, and Y. So L, T, and Y are stars that are named or termed as brown dwarfs. Brown dwarfs. And they are stars that don't have enough material to ignite fusion reactions in their very core. Remember what we studied in the sun. The sun is igniting hydrogen fusion reactions in the core, producing helium and energy. So these brown dwarfs, they don't have that much material, and that material cannot exert a strong pressure in the core that would allow them to ignite fusion reactions or hydrogen fusion reactions. It might ignite some deuterium, but not hydrogen. And those stars are not massive at all. Now, the spectral classification means what? Well, because if you observe the stars with the spectrometer, and what is a spectrometer? It's important for the exam. A spectrometer is a device that takes the light of a star and it spreads out and makes a rainbow. And if you look in detail in that rainbow, you are going to find a series of missing frequencies. So a gap, and we call that gap absorption, because the gas in the star atmosphere is subtracting that energy off the beam. So what we receive is the stellar rainbow depleted at certain frequencies because the atoms or the molecules in the star atmosphere, they subtract that out. They use that to provide them with energy so they can move around, they can warm up the gas, they can make the gas in this star stable. But these women, they classify the star by the intensity of certain lines. And now we are in a time in the history of astronomy that those lines were well known. So Bunsen and Kirchhoff, they knew that certain atoms like calcium, magnesium, and sodium and hydrogen, they produce certain transitions, certain absorptions, certain gaps that are so characteristics of them. And regardless if you are doing a spectrograph of calcium here in the United States, or in Russia, or in Japan, like with Salvador, or in any other part of the universe, so the element, the sodium, will show those typical transitions of itself. So when the gas interact, or when the atoms interact with light, there is some rules that are obeyed in this exchange of energy that provides these specific absorptions that we studied in quantum mechanics or in the atomic world. And that's how they were classified. So stars, there are all stars, they tend to have strong helium lines and somewhat weak hydrogen lines. But B stars, they have stronger hydrogen lines, and hydrogen line becomes the strongest in A stars. And then they start decaying, and so in M stars, they are not so strong at all. Okay. So whereas you can look at sodium lines are relatively strong in a star like the Sun. And our Astro 10L students, are now taking spectra of the sun and certifying and identifying these ionized calcium or these sodium lines and hydrogen line. They can see in the solid spectrum quite well, no problem in there. So basically, in spectroscopy, the science of spectroscopy is a science that, in reality, the stars talk to the astronomers, which is funny if you think. So you don't go to the star and collect a sample and bring to the laboratory. But because light interact with the stars out there, so when you collect this light, it comes with it information about the stars, as if the stars were communicating with astronomers, showing, revealing their inner secrets, in fact, inner atmosphere. And astronomers can use models, can use the laws of mechanical statistics, how light interact with atoms, what's the probability of certain transitions to occur. So they can use all of that information to explain how these lines are formed. And then we can establish educated guess on how the stars behave and how they are made of and all of that. Here's each stripe of this is a rainbow that indicates the strength of certain lines. And then you can see here, this is a hydrogen line in the red part of the spectra. You see the hydrogen line is not so intense in an O star, but becomes very intense in an A star. And then you start decaying. You still having a K5 star, but in an M star it's kind of a lost, right? I don't know what line is this. Looks like sodium line maybe. This is calcium. Calcium maybe? No, I don't know. In the calcium region. This is H alpha, maybe H beta. I don't know. But anyway, so I can see the scale there. I'm a bad spectroscopist. Where's the scale? I need the scale there.
The oxygen?
I don't know. That's a good question. If I bring that ideal, I'm not gonna do it. But your book, if you have the time, I really recommend that you read Voyagers in Astronomy. It's a very good piece of information, giving some hints on Ann Kenna. And she was so skillful in classifying stars that she was able to classify stars in seconds just by looking at spectra, and she could do it. And not only her, but several other women with PhD, very educated, but in those days, women, especially in science, couldn't get a job in astronomy. And so they were hired by 1/3 of the competitive price of postdocs, male postdocs, and they were much more efficient. And they were called or referred to as computers, the Harvard computers, because that's what they did, and they did very well. So we own them, the classification, the spectral classification of stars. And that's how pretty much it goes. Now, abundance. How can we mention and tell and discuss metallicity or abundance of different type of stars by studying in detail these little gaps? And we are not doing in this class, because this class, what is your job here? Your job is to understand how we build knowledge about the objects out there in the universe we haven't yet had the chance to visit, like stars, like galaxies, other galaxies. So you don't need to know the details on how these calculations are done, but you need to understand the tools, exactly what we use. So when you watch CSI crime scene investigation, right? and then you see the detective or the scientist collecting a sample of the blood, and then they go in a machine, they put the sample there, and what the machine does is vaporize, create a vapor, which means now we have these free floating atoms or molecules out in a gas, and then it shine a line through, and the light that is shining through the gas interact with the gas. Now it comes this law of the micro universe, the very little universe. Well, when you interact light with the little tiny suckers, the little tiny atoms, you do this interaction in a selective way, in a very selective exchanging way, in which energy, you cannot give energy. You give very select amount of energy, or you receive it from the atoms. And when this is done, you ended up with these gaps, and those gaps are called lines. And now, if you are definitely studying these lines, you can determine if they are symmetric, if they have a bump in the right hand side or left hand side in the blue or red shift, if they have central emission or they have central absorption, if they have all kind of things. And then the job of a student or a professional in the field is trying to interpret that. And to interpret, you have to use models. You have to make a model for the stellar atmosphere, a model for the light, and a model for interaction, and use the information we have about that interaction to build some sense. And then you create a synthetic spectra, and then you see if it matches your observation. If it does, probably your ideas are acceptable. It doesn't mean they are absolutely true. It means they are acceptable. Doppler shift. Doppler shift is very important. Oh, that is one of the most important tools astronomers have and make use in astronomy. So when you look at these lines and we observe stars, we don't see these lines always in the same position. They are slightly shift. And it is found if the motion between us and the object we are studying is such that we are approaching one another. These lines are shifted towards the blue end of the spectrum. Not a lot, just a small shift. Whereas if we and the source are moving apart, we detect the reverse. We detect what's called red shift. These lines are shifted slightly to the left, slightly to a longer wavelength. This is the so-called Doppler effect. It's not restricted to astronomers, because if you, like me, got a ticket in the last 10 years, probably that ticket was issued to you with Doppler effect. So we have a highway patrol kind of hitting most of the times, pointing one thing at the car, and what is being pointed is an infrared frequency, is like a laser source that is in the infrared, that goes to the car, bounces back, go to the receiver the officer carries, and when you compare the frequency that was sent with the frequency that was received, it gives a precise determination of the car speed. There is no contest. You cannot fight that one. It's very precise. In olden days, they would use not the infrared, but they would use radio frequency, which is much larger wavelength, and you could contest. You could say, no, what's the car next to me? Now there is no problem, because they shoot at your car with a very good precision. It's right there on the spot. Doppler effect, we can, all the motions, all the dynamics of the universe, including Big Bang, including the expansion of the universe itself, can be pretty much mapped by Doppler effect. And then we find that the stars are moving. They have proper motion. Big Dipper, this is an example of Big Dipper that today, 50,000 years from now and in the past, so the Big Dipper is changing. I mean, it seems to be the same because, year by year, the stars are so far away and they are so far apart that we cannot measure or perceive how they smear away, how they kind of lose their shapes. But if somehow you have enough money to freeze yourself in some weird technology and works, and you are waking up, let's say, a few 100,000 years from now in a different civilization, I don't know if somebody want to do that. Perhaps the sky might be slightly different. Um, some stars might be dead, and but certainly the constellations might have changed because they have what's called their proper motion, and this proper motion can be measured and mapped with the use of Doppler effect. So Doppler effect allows to measure this thing here, radial velocity, right? Radial velocity is the velocity in respect to the line of sight connecting the star itself and us. The velocity that is perpendicular to the line of sight we cannot measure with Doppler effect, but we can see the star moving. We can see the angle here, the so-called proper motion, and this proper motion plus measurements about the star brightness can indicate the direction in which the star itself is going. Rotation, for instance, Mercury rotation. Astronomers in the end of 1800, 1900, they were trying to use telescopes to measure the rotation of Mercury the planet. The same way that they were trying to measure rotation by observing Mars. So if you take the telescope and point at Mars, you can see features. So if these features change position over time, you can address a rotation for the planet. But Jupiter was complicated. We couldn't do with Mercury, I mean, because Mercury has the features were not well mapped, first of all, and Mercury is always closer to the sun. So when you start observing, the sun comes in, or Jupiter settles down, and then we don't see anymore. It's complicated. Now we have a precise measurement of Mercury rotation because of Doppler effect. So Mercury reflects the sunlight, so the sunlight goes to Mercury's surface. So as Mercury rotates, part of its hemisphere moves away from us, and part of its hemisphere moves towards us because the planet itself rotates. And this rotation smears out and broadens these skinny absorption lines that comes from the sun. So you have a skinny line or signature that goes to Mercury, but some of these lines falling on a part of the hemisphere that is going towards us ended up being blue shifted. And the part of the sun's line or feature that falls on the hemisphere that moving away is red shifted. So when you combine those two phenomena together, you can now you have to use some theory or something, but you can get some precise determination of Mercury rotation, Doppler effect again. But that's it. Those are the main ideas. If you in the following chapter 18, it discusses how consecutive observations of binary system can tell you about the size of the system itself. It can tell us by use of Newton's law what is the total mass of that system. Using Kepler's law or Newton's law, we can only really measure masses if we observe the stars in a binary system. Otherwise, we can't. So the next chapter is an extension of all these elements we study here, but applied to objects that are binary, and but pretty much the core is in chapter 17. So next week we initiate stellar evolution. So what happened when the fuel, the hydrogen fuel in the core is exhausted? So what's going to happen with the star? And then we realize that our lifetime of 100 years, if you will, is nothing compared with the lifetime of stars, but stars do pass over, or the stars do die. I mean, die or death is a word used in a biological sense. Stars are not biological beings, but they formed and they end their lifetime. And as we learn, the important aspect of stars is to produce atoms. So stars, with the exception of hydrogen and helium, stars produce all the other atoms, either by when they explode as supernovae, or as when they create cosmic rays that create certain types of atoms in the interstellar medium. But the stars either synthesize atoms when they are, pretty much during their lifetime, or they produce atoms when they explode in supernovae events, or and some of these particles might help to create other atoms in the interstellar medium. And stellar evolution is a fascinating object. Is a fascinating application of the laws of thermodynamics, lots of physics, and how gas behave in response to energy input. And so it's exciting to advance to that part of the course. And I will next week play some simulations, because the NAAP simulator has a very good one on HR diagram, which is a evolutionary diagram which score in our course. Okie doke.
Okay. So for the midterm, it's just going to be chapter 4 and the sun.
No. And everything in between.
Between.
It's a sandwich. You are only mentioning the bread part.
Okay.
Yeah. So in between enters formation of the solar system and few characteristics of terrestrial planets and Jovian planets. Don't worry about too much detail, but you have to have some major notion of it.
Okay.
You can use a cheat sheet. Yeah. And take your notes. And as I mentioned, together with the cheat sheet of midterm 1. So, and when we go to midterm 3, we have another one. So you have a collection of 3 cheat sheets that you can take to your final exam. So don't throw them away. Just save it.
Okay.
All right? Okay, fellows. That's it.
All right.
Any other
you.
question? No?
No.
All right. Good night to you all.
Good night.
Good night.